let's try to understand what is a probability distribution. We have seen about random variable. We have understood what is a probability. We have compared it with statistics. Let's see what is a probability distribution. So it is nothing but a list of all possible outcomes of a random variable. When you roll a die, you get different outcomes. All those outcomes, if you make it as a list, that is a if you make it as a list, it becomes your distribution. It means that random variable, its range. Generally, in mathematics, we talk about range and domain. Same way, for a random variable, its range is its distribution. Okay, so list of all possible outcomes of a random variable along with their corresponding probabilities. So this is the possible outcome, its probability. So these are all the possible outcomes and their probabilities. This is your probability distribution. So the list of all the values, all the possible outcomes along with their probabilities is called as probability distribution. So let's see an example here. This example which you are seeing here, it is a discrete univariate probability distribution. So why we say discrete, why we call it as univariate with finite support? Let's try to understand it. So you understood discrete variable and continuous variable. In discrete variable, it is finite and countable. Discrete variable, right? So for a discrete random variable x, p of x denotes the probability. P of x denotes the probability. That means for this random variable x, the probability of getting this x is denoted as p of small x. Okay, that p of x equal to x. This is what we have been studying till now. We have studied already that x equal to x means probability that this random variable or this experiment will get the value of x. What is the probability of getting small x as the value for this random variable x? Okay, this x denotes the random variable. Maybe in the experiment what we have done, what is the probability of getting when I have 10 MCQ questions and each one mark. In discrete case, I may get marks from 0 to 10. So what is the probability? My x is here correct questions. Okay, x is here correct questions. So my x, this will be, what is the probability? What is the probability of getting 3? It means 3, what is the chance of getting 3 as the marks? 3 questions are right out of this 10 MCQ questions. Okay, so for this discrete random variable x, this you understood, this notation you understood. P of x equal to s is the probability of getting small x as the value for this random variable x. In this case, for this p of x denotes the probability that p of x equal to x. This p of x is called your probability mass function, PMF. Okay, p of x is your probability mass function. We use this probability mass function notation to show the probability. For example, let's see here. See, p of x greater than or equal to 0 or less than or equal to 1. Okay, so for all values of x, generally this p of x is the probability. P of x is the probability. My this case, no, p of x equal to 3 is also same as p of 3. What is the probability of getting 3 for this random variable x? So this p of x notation, we use it here. We call it as probability mass function. So, and also we have studied that the sum of all the outcomes of the random variable is equal to 1. So the probability can range between 0 to 1. It can range between 0 to 1. Right? That's what. It is represented as probability mass function. So the p of x value can be greater than 0 and it is less than or equal to 1. And when you do summation of that, it should be 1. When you do summation, see this die example, if you take dice, I am rolling 1, 2. So what is probability of 1? What is probability of 2? Probability of 3, so on, probability of 6. This is a probability mass function. This also can be written as P of capital X equal to 1. This is the probability mass function. The summation of all these probabilities is equal to 1. Okay. Discrete probability distribution example. Let's see this example. When you toss two coins, count number of tails. You're tossing two coins, count number of tails. So I have two different coins. I'm tossing them. You see, when I'm tossing them first time, how many times am I getting? Here both are hits. Here both are hits. Number of tails is zero. When I'm tossing it for a second time, one head, one tail. So number of head is one. When I'm tossing it for the third time, when I'm doing it for the third time, I'm having one head and one tail. I'm having one head and one tail. So I get the value as 1. And in the last case, if you see, I'm having both the tails. So number of times I get tail is 2. Number of times I get tail is 2. Right? Now if you compare here, two coins I'm tossing, I'm counting number of tails. So I can get 0, I can get one heads, or I can get one tail, or I can get two tails. What is the probability of getting 0? That is 1 by 4, because this is one case. I'm getting one case where both are 0. 1 by 4, that is 0.25. What is the case of probability of getting value one tail two times? That is 2 by 4. So 1 by 2, 0.5. What is the case of getting two tails? It is two tails is one time. It is getting two tails is one time. That is 1 by 4, 0.25. Okay. So this is your probability distribution. Why? You see how you are writing it? You are writing the possible outcomes along with their probabilities. So somebody asks you what is the probability distribution when you toss two coins, means this is the data for that. So you have the x value, small x value, and you have their probability of x together. X and P of X. It means getting one tail, zero tail, one tail, two tail. And what is the probability? 0.25, 0.5, 0.25. These are the, this is your probability distribution when you toss two coins. So if you visualize this, if you try to see in a kind of table, we try to draw same thing, getting zero tail, one tail, two tail, its count is this and its probability is this. Okay. And if you draw a graph and see, getting 0, it is something like this, getting 1. So just pictorial representation, visualizing the discrete probability distribution. Again, we have continuous probability distributions as well. We'll see that. So this is the formula. We'll ignore this now. For now, when we see the types of probability, we'll come to when we see types of probability distributions. Now try to understand what is a probability distribution. It's a kind of a table or a collection of data of the possible outcomes along with their probabilities. That's it. You remember. Now, next one, continuous probability distribution. So, discrete probability distribution, if you see, if I'm drawing it, it's something like this. It's fixed point. Then again, I have fixed thing and I have fixed thing. It contains straight lines here. Whereas when you go for continuous probability distribution, in discrete case, let's compare the probability distributions of discrete and continuous. In discrete case, we already know what is discrete random variable. This set of outcome we already know, and it is fixed. It is limited and countable. Whereas in continuous probability distribution, in continuous, it means a probability distribution for a continuous random variable. What is the probability distribution? Collection of the outcome along with its probability. So this is the outcome along with its probability. This outcome belongs to which kind of a random variable? That is a continuous random variable. So for a continuous random variable, a probability x equal to x is meaningless and 0. Why? Because you do not know this x. You cannot know about x. You cannot, in continuous probability, you cannot write like this. Why you cannot write like this? Because you do not know x. X can be anything. In the previous case, why I wrote like this? Because I know x can be, when I am rolling a die, x can be 1, x can be 2, x can be 3 or 4 or 5 or 6. But if it is a continuous random variable, I do not know what is the value of x. I do not know what is the value of x because it can be anything, any 0.05, 1.5, 0.3, 0.7, 15.2, any number. But what I can give one thing, but how do we quantify it then? In continuous probability distribution, we give it as a range of values. We say that this x value can be between 5 and 7. Like this we represent. Okay, so sometimes if the probability is written like this, x is equal to 3, this is a discrete random variable. It's a discrete probability distribution. If you write the probability something 4 less than or equal to x less than or equal to 7, it is continuous probability distribution. This x is a continuous variable, random variable, whereas this x is a discrete random variable, right? Because I cannot write this way, because this x is unknown to me. It's infinite, uncountable, and I cannot predict it. I don't know what is the possible outcome. It can be anything. I cannot guess it. It can be anything. So instead we use f of x to denote probability density. Okay, and is often expressed in terms of integral between 2 points like this: p of a less than or equal to capital X less than or equal to b. It means this random variable x can have any value between a and b. This is possible. This we can try to predict. Why? We try to visualize that particular probability density function, and we can tell it. We'll see examples about that. So for a continuous random variable, we can only talk about probability within an interval. We can only talk about the probability within an interval. That is something like this, A, and in between B. Whereas in discrete, I can tell it like this, right? So see this example, metal cylinder production example, metal cylinder production. Suppose the random variable X is the diameter of randomly chosen cylinder. X is the diameter of the randomly chosen cylinder. Since this is a random variable, it can take any value between 49.5 to 49.5 to 50.5. Since if it is taking any value between these two, it's a continuous random variable. If it exactly it is 50, I say it is a discrete random variable. Okay, we'll see problems on that. So continuous probability distribution, we are saying it, we are representing it as a function p f of x, whereas discrete I am representing as p of x. Okay, I'm using this function p of x there. Probability mass function. Here we say probability density function. Mass function and density function. It has to satisfy these two properties, that f of x has to be always greater than 0, and integration of this x f of x dx should be always 1. Integration of this x is the range a to b, integration of this f of x d of x between this range a to b should be 1. That is the condition here. Okay, so this is just an example. We said, right, metal cylinder x is a continuous random variable. If you take the diameter, if this represents the diameter of a metal cylinder, that is 49.5 to 50 point. Just an example. Metal cylinder is just an example. So we say this is a continuous random variable. It can take any value between 49.5 and 50.5. It can take any value between these two. Okay, this way. Suppose this f of x is given as like this. Suppose f of x is given as 1.5 minus 6 into x minus 50.2 whole square. Assume that the probability density function f of x for a continuous probability distribution is given as this function 1.5. This is just an example, x minus 50.2 whole square. If f of x, what is f of x? Probability density function. Why are we talking about probability density function? In continuous probability distribution, we represent, see, I will just go back to discrete. In discrete probability distribution, we say that it's a combination of its outcome along with its probability. We are representing it as a table. Whereas in continuous probability distribution, we represent it as a function f of x. 1.5 minus, this is the function given. And what is the range given? This one, 49.5 to 50.5. In this case, if you apply, what is the condition here? Condition for this f of x to be a continuous probability distribution, condition is that f of x should be greater than 0 and integration of f of x should be 1. So if I see here integration of this is A, this is B. If I do integration, you know how to do this integration. Substitute these values in these both, you get value as 1. Okay. So this is, we can say this function, this example function is a continuous probability distribution function. Right. Now see, the probability of the metal cylinder has a diameter between 49.8 and 50.1. Now they are saying, see, in continuous probability distribution, we always represent between some value like this. We represent as a function f of x. F of x is your continuous probability distribution. For a particular problem, for any particular problem, given f of x equal to 1.5 minus 6 into x minus 50.2 whole square. This is just an example one. We are saying this f of x is a continuous probability distribution function. For this, we are giving two range of values a and b like this. For this, you try to verify and see, we get the values 0.432. Integration of x, f of x, d of x is not equal to 1. If it is not equal to 1, it means this a and b, this x is a continuous random variable. It is taking two values. It is taking a range of values between 49.8 and 50.1. Okay, 49 and 50.1. So this function f of x is not a continuous probability distribution function. That's why it is failing. Okay. Now let's see this very important classical example classification problem. We'll try to see how we use probability distribution functions or the concepts of probability in machine learning. The classical problem is classification. Classification is one particular algorithm or one particular important concept in machine learning. So how probability and its probability distribution functions are used in solving a ML problem, let us see. Okay, what is the problem? Let's try to understand the problem. It's very interesting and important example. With this, we will be you will understand why are we studying probability and probability distributions for machine learning. So given a collection of data of two different insects, katydids and grasshoppers. There are two different insect data set is given to us. Okay, decide what type of insect the unlabeled data is. Okay, you have some examples of katydids, you have some examples of grasshoppers. This is already given to you. Now given a new insect image, you have to classify whether it is a katydid or it's a grasshopper. Okay, you have to identify whether it's a katydid or a grasshopper. That is the problem. This is a classification problem. I want to classify this whether it belongs to type A or type B. Type A is katydid, type B is grasshoppers. Now a new image is given. How we generally do it? What we try to do? We try to identify its features. We try to extract its features. So like this, what are the features? Abdomen length, thorax range, the spiral diameter. Here we have some spiral, the legs length, then antenna length, this antenna, does it has wings or not? Okay, what is the color of the insect? What is the color of the insect? Okay, we try to analyze its features. That features form your data set. That features only forms your data sets. So we try to extract the features from the insect. Okay, then see, let us take only two concepts now. So I have, this is my existing data. This is my existing data. What is this existing data? This is what is given to us. Type A and type B are given to us. From these, we extracted some features. What are those features I extracted? We extracted so many things from that. From those images, from those data, we extracted so many features. Now, I am taking only two such features, abdomen length and antenna length. These two are sufficient. We have already studied how to consider two important features. There are a lot of features which are too important that we have considered. Okay, so abdomen length and antenna length. So for insect 1, if it is 2.7 and 5.5, it is of type B grasshopper. Okay, so if it is 8 and 9, it is catedid type A. So this is the data we observed from the given data set what we had here. We tried to extract their features. After extracting their features, I got this my table. This is your regression data, right? You have some existing data, not regression data, your ML data. You have some existing data with you. Using this data, okay, now suppose I give some abdomen value and some antenna length. What is the type of insect? So this is my abdomen length and this is my antenna length. Now now classify if some insect, if it has abdomen length as 5.1 and antenna length as 7 mm, then what is that insect? Whether it is of class A or class B, whether it is catedid or grasshopper, that I have to find out. Let's see how we use probability concepts here to find out whether this given data, which is unseen data before, is a grasshopper or a catedid, type A or type B. So we try to see the abdomen lengths. We try to plot. That's why data visualization is very important concept in data science. This is very important step. See how we are doing it. Antenna length, abdomen length. I try to plot antenna length and abdomen length. I try to plot. You could see abdomen lengths. Okay, abdomen lengths are all here, whereas antenna lengths are something like this. Okay, so this is just for classification. We have just plotted. Okay, for grasshoppers, the antenna length and the abdomen length ratios is this, which are low. It means for grasshopper, the abdomen and the antenna lengths are small, little smaller values. Whereas for catedid, the abdomen length and the antenna length is high. Okay, this is just to do some visualization. Try to understand. Now let's go to next point. Let's see. Again, if I plot that into a graph, I get the value something like this. And if I plot those distributions, see, I have plotted their distributions. It is something like this. What does red represents? This is about the catidids. This is about the grasshoppers. So the grasshoppers data, the catidids data is something like this, and the grasshoppers data is something like this. Okay, so we could see two normal distributions. It means for catidids, the length, the antenna length, and the abdomen length are high, whereas for grasshoppers, they are low. Maybe you can see this data set. See, abdomen length 2.7, 0.9, 1.1, 2.9, 0.5, which are all less than 5. It is grasshopper. See, other case you see 8, 5.4, 6.1, 8.3, 8.1, which are above 5, they are catidids. Okay, so I am trying to represent them. We can leave the histograms as we can summarize as two normal distributions like this. Some features are matching, for some they are matching. Now, see how we use probability here. This is the given question, right? We are given this. Sorry, I'll go back here. This is our insect now. Find out what it is. Is it of catedid or grasshopper? So what we try to do? We will try to classify the insect. Its antenna lengths are 3 units long. How can we classify it? If its antenna length is 3, how can we classify it? Tell whether it is a grasshopper or catedid. So we can just ask ourselves, given the distributions of antenna lengths, we have to see, is it more probable that the insect is grasshopper or catedid? In terms of probability, if I ask the question, it is P of Cj given D. Given the D, that is the length of the antenna, what is the probability that this insect belongs to class Cj? It belongs to type Cj. Cj is the class. Okay, so see here, these are the distributions. This is the point which I am asking you. At given the antenna length as 3, what is the insect? So what is the region it is covering? If you try to draw a line here, if we try to draw a line here, in this distribution, this is very small value. Whereas in this second distribution, this is a very large value. So by this, you can guess, right? It's a grasshopper. See, grasshopper, given its antenna length is 3. So what is, see, in this line, in this probability distribution of grasshopper, this 3 is matching it here, this point, that is 10. Okay, this point value is 10. So 10 divided by 10 plus 2. Why 2? Because the matching point here is 0.833, whereas for katydid it is 2 by 10 plus 2, it is 0.166. It means given antenna length as 3, probability that it belongs to grasshopper is 80.833. We are not sure. We cannot say whether it's a katydid or grasshopper, but we can tell in terms of probability that given antenna length is 3, the probability that it belongs to grasshopper class is 0.833. The probability that it belongs to katydid class is 0.166. There is a difference between both. Let's take another example. Okay, now the given antenna length is 7. Given antenna length is 7. So if I draw a line here, what is the point on this? It is 9. The point here on this is 3. So the probability that it's a grasshopper is 3 by 3 plus 9. So we get 2.250, and 9 by 3 plus 9 is 750. It means given antenna length of 7, probability that it belongs to katydid class is 0.75. Kind of I will say 75%. I am confident that the antenna length given 7, it is a katydid. I am 75% only confident. That is in terms of probability. I hope you got now how we are using that probability distributions. When continuous probability distributions, when they are represented as a function f of x, we are trying to find out the probability. Okay, so if we quickly summarize what we have seen, so these are few basic rules which exist in probability, which are useful for us. These rules are useful for us in next concept like finding out variance, covariance of solving different using probability for solving different ML problems. Okay, we'll come back to this and we will see these basic rules, right?